Hello everyone and a very warm welcome to this week's long tip. I am very happy to say that I made up my mind how to call those tips or tutorials based on the length. So we are calling it a quick tip if it's under 10 minutes. Then if it's under 20 minutes, we are calling it a quickish tip. And if it's over 20 minutes, we're calling it a long tip. Hopefully you're fine with that. But back to the topic, we are in the part 2 of our diamond series where we are going very nerdy about materials. So last week we modeled our gemstone and did a test if it was modeled correctly to the spec. And indeed we found out that it was an excellent cut. So this week we're going to dissect aberration or dispersion, how it's called in Octane, and we are going to dive deep into wavelength, colors, and material theory when it comes to refractive materials. And I promise you there will be something in for you even if you don't render with Octane. So let's dive in and let the fun begin. So I've opened up the scene from last week where we finished modeling the diamond. So let's create a small scene around that in the terms of creating two HDRIs. So let's do this by going to the TUT recording layout so we get our Octane setup. Alright, first of all we want to toggle the info so it's off. Here we go, much better. And then we are going to create two HDRIs. One will be an HDRI where we actually load an HDRI image in here. And what better to load than again Maxim Ross's HDRI. Shout out to him. And to make the backdrop not show the HDRI, we are actually going to create a solid background by going to the other HDRI and making this value rather dark, so 0.05 for all the RGB channels. And then in the HDRI, let's set it to visible environment. Let's render to check if everything's working out correctly. Yes, this is the expected result, so we can carry on creating the diamond material. Small interlude to put things into perspective. So if we are looking at the whole range of frequencies in our universe, what our eyes can see is basically a fraction of those. So if we are looking at this fraction, you can see those are the colors we can perceive. And basically this is everything we are doing with materials inside of 3D software, simulating light so we can perceive something with our eyes. Now back to the scene. In the scene, I want to create a specular material. We can easily do that by going to Materials, Create, and then go to a specular material. Here we go. Let's call that material diamond and change the values so it becomes a diamond. So first of all, as always, let's go to the transmission and set this to 1. Because the loss of energy comes normally from absorption and not transmission, and diamonds have a very negligible amount of energy loss, so we can leave that out completely. Next, what we want to do is take care about the index. I told you that the index of a diamond was 2.417, but where does this value come from? So the index value here is also called IOR, Index of Refraction, or ND. And it defines the density of the material for the light. So light is traveling, of course, with light speed, but if it's entering that material, it will be slowed down, and it will be slowed down by the factor here. So the light speed divided by this factor. And this makes the light also refract. But again, where do I have this number from? Actually, there is an internet site that is very useful when it comes to physical correct modeling, and this is this site here. This site is called refractiveindex.info, and it gives you all sorts of usable knowledge about physical materials, mainly stuff that is related to the Fresnel equation as the IOR or the extinction coefficient value here. So let's search our diamond value inside of the site. So what we want to do is go to 3D artists. So we get a more easy to phrase list here, and we go to crystals. And the first crystal that pops up is already the diamond. Now there's one more thing you need to do, and this is select the right wavelength here. And you do that by going to the line select and select the D line here. Here we go. What makes the D line so special, you ask? Or what are lines anyway? So there was this guy Josef Fraunhofer, and he did some experiments with the sun, basically splitting up the sunlight in a prism into its components, meaning the rainbow colors. And he actually discovered some dark spots within the spectra. So he classified those and gave those lines names, and this is then what became Fraunhofer lines. There's of course, as always, much more to that, but I have to cut it short to not make a 1-hour video here. So some of the lines have stuck with the science community and are used later on to measure stuff and have a fixed point in the spectra. So for the diamond, this is the D line. Spectrometers that measure the refraction of objects have used that wavelength. So this is also the reason why this wavelength has carried over to 3D as the main wavelength when you're looking for the right IOR. Okay, so now that was a lengthy explanation here, but we finally figured out our N value here. This is the refractive index and it's 2.4166, and if you round that you have 2.417. So we can even be more precise by copying that value and pasting it over there. Here we go. And then if we assign a material and render, you can see now we have a sort of good looking diamond. So if you're after a non-dispersive diamond, you're actually done here. You have finished and made a great diamond model with a great diamond material. But ahead of us lies the big universe of dispersion. So let's dive in and actually go to the dispersion tab here. Now the dispersion value is a dispersion coefficient that can be set with a number here. What you need to know is there are different ways to calculate dispersion. What is used here is the Cauchy equation. So Augustin Louis Cauchy was a scientist in the 1800s who discovered a way to calculate the dispersion in the visible spectrum. And this is still used today in some 3D applications. Obviously, we can go about it artistically and then just slide the slider around and get the desired value out here. But we want it to be physically accurate, remember? So let's do this the right way. And actually, this is where I need to bring in some helpers. Here we go. So I've made some espresso setups that help us to determine the right dispersion. Again, with the help of the refractive index site. So let's bring this up one more time. So I temporarily changed the layout so we can more easily change out the data. So let's show you first and then we talk about what we do here. So those are values we need to copy and paste over here inside of the wavelength and then copy back the value that the site here spits out for us. And down here again, we can copy those values into our dispersion, into our Cauchy B equation, and into our IOR. So let's get this locked here, and we now get to our dispersion, copy that, and to our index, copy that. Here we go. So what have we just done here? So basically what causes dispersion is that the stone, the density of the materials varies per wavelength of light. So if I click on the log X to emphasize this portion a little bit more, you can see that with the wavelength here shown in micrometers is changing in the IOR. And this basically creates our dispersion. So we are again sampling 3 Fraunhofer lines here to have 3 different wavelengths, and therefore we can have some clever math involved that then gives us our Cauchy dispersion and some Abbe number. We will be talking about that a little bit later. Hopefully you're still with me, so we get out our dispersion value that we can then take to our material. But why is there another index value here that we also need to plug in here? To explain that, I invite you to follow me into Testland. So I did those renders with the magnifying glass you already know from the intro animation. So as you can see here, I increased the Cauchy B number without altering the refractive index. And what you can see is that actually increasing the Cauchy B also increases the refractive index. So you're basically changing the refractive index by increasing the dispersion. Obviously, we don't want that. We want the refraction to stay the same. We just want to increase the dispersion in the stone to a natural measured level. So since the Cauchy B is increasing our refractive index, we actually need to compensate by lowering our refractive index the higher the Cauchy B value is. So why is that even so complicated? The answer is that there is also a Cauchy A value that is also an index. And the Cauchy A value, which is the index, and the Cauchy B value, which describes the dispersion, are belonging together. So what I did with my espresso is I calculated the Cauchy A value from our initial index. So the Cauchy A value drives our index, while the Cauchy B value drives our dispersion, and together we get the right result in a non-changing index with changing dispersion. And this is also the answer why we need our formula to not only calculate the Cauchy B, but also a different index or IOR. To maybe gain a little bit of a better understanding, I did that same test with a little bit of a simpler scene, namely a prism. So here you can see the uncompensated version, where we can see the whole dispersion is skewed to one side and is not centered. While here you can see the centered or compensated version, where the dispersion runs around the center of the initial IOR and it does not skew to one side, which is much more preferable. So let's actually show this to you in a more visual way. It's basically charge time again, but this time within Cinema 4D. There's always something new, isn't it? So what you see here is a camera ray that is refracted through our prism here. And then we have a reflection ray for the sake of being correct. But this doesn't matter in our calculation right now. So when we hit our prism here and turn up the Cauchy B, what you can see is that the dispersion actually grows off into one side. So if the number of our floor grid was here, you can see that the rays actually disperse in that direction. So for our camera, it looks like the number is changing into the opposite direction. And therefore, we get the result we just saw in the animation of our prism. Now, if I go ahead and correct the IOR for that, you can see now, if I go from 0 to a higher dispersion value here, the dispersion revolves around our original refraction, which is much more natural and what we actually want when we dial in dispersion values in our materials. We are back at the main layout to actually answer one of the questions that popped up before, and this one is about the Abbe number. Why is it in here? As I mentioned before, there are multiple ways of calculating the dispersion of a material. And besides the Cauchy B, there's actually the Abbe number. So after Augustin Louis Cauchy developed his formula to calculate the dispersion, Ernst Abbe came around and improved upon that, mostly by improving the accuracy outside of the visible spectrum. And this is the reason why also the Cauchy equation is still used, because within the visible spectrum there's sort of the same accuracy for both. So if you're working with other renderers such as V-Ray, Arnold or Redshift, those all use the Abbe numbers instead of the Cauchy B equation. What might surprise you is that Octane has one of its own materials also using the Abbe number. So let's create one of those materials by going to Material, Create, and actually create a Octane StdSurface. Here we go. So inside of the standard surface, let's shift some things around to make this a diamond material. First of all, we want to go to the transmission layer and set the weight to 1. And then we go to the specular layer and there set the roughness to 0. Here we go. Next, we want to change the IOR to 2.1466, as we've learned that is the correct diamond refraction value. So if we go over to the transmission layer again, if you look closely, you can see there is the dispersion Abbe number here. But before we sign that in here, let's actually apply the material. You've seen that something has changed here, and this is due to a small bug inside of the material. I am positive this will be fixed in the future, but for now I urge you to use the old material system in Octane until it's fixed. It has something to do with the internal reflections, so let's fix this for now real quick by going to the geometric properties and set the opacity to 1. There's still a lot of quirkiness going on, so if I re-render, the internal reflections are gone again, as you can see, and I need to wiggle around with the opacity to bring it back. So don't use the material for now. So let's actually go back to our transmission layer and play around with the dispersion. So 0 is the value for turning off the dispersion, but it is the other way around than the Abbe number. So if we have a very low number, we have a very high amount of dispersion or aberration here, and the higher the number goes, the lower the dispersion becomes. So if we go to our calculator once more, we can copy out that number and paste it into our diamond material here. And if we now save that in our picture viewer, and then go to the other material where we calculated the Abbe number and the right IOR, and also copy that to our picture viewer, you can see those are almost identical. So as you can see, a huge advantage of the Abbe Numbers system is that you don't have to correct your index. So the Abbe number does the calculation for you, and the dispersion revolves around your initial refraction, so you don't need to calculate your way around to a Cauchy A, and you get the expected result right away without any further work. So you can also use them in Arnold, V-Ray, Redshift and all the other renderers that have Abbe numbers instead of the Cauchy number. Alright, for the completeness sake, you of course not only can do diamond materials, but also all sorts of transparent or refractive materials, as for example glass. So let me demonstrate this to you. It's basically the same workflow. In the refractiveindex.info site, we go to glass, and then we choose a glass type here. There is a plethora of glass types available to choose from. We will go with the shot glass right now. So you can see with a lot of those glasses, there's already a Abbe number here, so you don't have to calculate that. But I want to show you the calculation anyways. So again, let's go with those 3 numbers and type them in here, and then go and paste back the N number to the respective position in our calculator. I don't know why the Abbe number never matches exactly, but since we're dealing with a very high number here, we don't need that much of a precision. But anyway, if you are a mathematician or a scientist and know how I can get my formula to be more precise, please reach out. I'm happy to update that. So now that we've calculated that, you can type in the values into your Octane material and then have the shot glass here with the right dispersion and the right index. Alright, for the last section, the keen-eyed among you might have spotted that I pasted in 2 formulas here. So the second formula is a formula for the people who want to dial in the refraction values artistically and then get the right dispersion or Cauchy B formula on top of that. So let me just show you by going to my material here and dialing in the index so we can have a nice magnifying glass effect. So let's actually go with that value, 1.65 for example. Let's say we are satisfied with that. Now, of course, again, if we go to the dispersion over here and set the dispersion value to our liking, we are adding on top of our refraction, which we don't like. So let's say we somehow dial in something where we like the dispersion of it, so 0.02. That's great. But now we want to get our initial index back, so the way it looked without the dispersion. And this is where index corrector comes in. So we have our index that was 1.65 and our dispersion which was 1.02. And this gives us the new index here. And if we paste that back into our index, you can see we get our old index, so the behavior is the same that we had without the dispersion, but instead we get the nice dispersion on top. Now what this also gives you is a rough estimate of the Abbe number here, and this is basically useful if you want to convert Octane materials, for example from an old material to a standard material, or if you want to convert your Octane material to an Arnold or Redshift material that is using the Abbe numbers. Alright, that was quite something, wasn't it? A lot of research went into this episode of our long tip here. I hope you enjoyed it and can actually do something with all of the knowledge provided in that video. As always, a small shout out to myself. I do trainings and courses on-site as well as online. If you're interested in gaining more knowledge about the 3D space or bring your team up to speed, especially about materials, you can contact me via mail. I initially wanted to include lighting in this tutorial, but the part of the dispersion took so much time away that I left it out. But basically, lighting diamonds is not a very big task. If you're down for a third part about lighting, let me know in the comments. If there's enough requests, I'm inclined to do that also. And that leaves me with my last words. Thank you very much for staying with me so long. Thank you very much for your support. Hopefully see you next week. Cheers and happy sparkling. Bye.